Well, hello everyone. My name is Alfredo Rivera. I am an account manager with BAC's commercial refrigeration team. And today I wanted to talk to you guys about BAC's Trillium adiabatic cooling product. We have a quick presentation today, so I'll move pretty quick through most items, but I just wanted to spend a couple minutes talking about condenser options that are currently available. Spend a little bit more time talking into the specifics of how an adiabatic product operates, highlight what makes BAC's Trillium product different from other adiabatic products currently available, look at some examples at how I see our customers using adiabatic in specifically CO2 systems, one as a cascade example, and then also in transcritical, subcritical operation. And then last, just talk about some of the opportunities that adiabatic can provide in terms of retrofit for existing supermarkets. And I have two quick case studies to highlight those specific opportunities. So traditionally, we've had two choices when it comes to choosing condenser equipment. Air-cooled equipment that tracks dry bulb temperatures, which typically means larger compressors and more energy use year-round, or evaporative condenser products, which tracks wet bulb temperatures, which allows for lower condensing temperatures, smaller compressors, lower energy use, but does come with the need for additional maintenance in terms of water treatment. So let's look a little bit more specifically at the air-cooled option. Air-cooled condensers are simple and require very little maintenance. Typically, they are a very low first cost option in terms of your initial capital investment. They work by drawing ambient air across the refrigerant coil. So for this reason, they're limited by the ambient dry bulb temperature. In most cases, designers are designing for 100-degree days or sometimes even higher. So that translates into design condensing temperatures of maybe 100 or 115 degrees. Those high condensing temperatures mean larger compressors, more compressor energy. Typically, we also need a large volume of air for this heat exchange to happen. So that means high fan energy and high noise. And along those same lines, we need a lot of surface area on the coil to achieve this heat exchange. So large surface area on the coil means large footprint in our equipment. Evaporative condensers work by spraying water directly on the heat exchanger, typically the refrigerant coil, but it could be a water coil in case of a fluid cooler application. Heat is removed as the spray water evaporates off of the heat exchanger. So the capacity available is based on wet bulb temperatures, not dry bulb temperatures. Wet bulb temperatures, you could think of it as a measure of the moisture content of the air. Wet bulb temperatures will always be lower than corresponding dry bulb temperatures. And for this reason, most evaporative condensers are allowed to design for condensing temperatures around 95 degrees or sometimes even lower. These lower condensing temperatures mean smaller compressors, lower compressor energy. And using the evaporative cooling effect of water means we need less air volume, so smaller fan energy, less surface area, a smaller coil, which translates into a smaller footprint. There are some costs associated with the benefits that come with evaporative cooling, and these include high water use and the need for chemical treatment. Evaporative cooling products feature large sump basins and spray water distribution that may produce aerosols. And for this reason, chemical water treatment is needed for biological growth control and for scale prevention on the heat exchanger surface. Adiabatic products feature a dry coil and adiabatic media pads that are located outside of the coils. Water is distributed over the pads, and the fans pull ambient air across the pad media. This air is cooled as water evaporates off the pads and it's pulled across. This cooled air then reaches the dry coil for the heat exchange process to happen. This allows adiabatic products to be designed for condensing temperatures similar to evaporative products. Also, they feature small footprints similar to air-cooled condensers, but much lower water use than a similar evaporative condenser, and no chemical water treatment is required with an adiabatic type system. Now let's just look a little bit more at the modes of operation for adiabatic coolers. In its most simple form, it runs in dry mode. This is when ambient temperatures are below the designated wet mode switch point. This switch point is field adjustable, but BAC recommends using the mean coincident wet bulb associated with your design day conditions. So when ambient temperatures are below this mean coincident wet bulb temperature, your unit operates essentially as an air-cooled condenser. No water is used. The variable speed fans will modulate to meet capacity based on the load and the ambient air conditions. As ambient air temperatures rise, once it meets the design mean coincident wet bulb, then pre-cooler mode is activated. Water is distributed over the pad media, and the adiabatic cooling process takes effect. As air is pulled across the pads, it is typically cooled to within about 2 to 3 degrees of the wet bulb temperature. This allows for lower condensing temperatures, maximum compressor energy savings, and the fans, again, will continue to modulate to meet the capacity based on the load and the ambient conditions. Water in the recirculating system is drained periodically and made up with fresh water to maintain water quality. BAC's Trillium adiabatic product is available in 2 distinct configurations. One is with fan models from 1 to 4 fans in a single row arrangement, and then larger capacity models available from 4 to 14 fans, with the unit being 2 fans wide. Various coil configurations are available across the product line in terms of both multi-circuit coils, ammonia coils, high-pressure CO2 coils, and standard HFC condensing coils. What makes BAC's Trillium product different from other adiabatic products on the market? It's all centered around our water distribution system, the water sump, and the recirculating pump. In order to experience the benefits of adiabatic cooling, your unit needs to be running in wet mode. Otherwise, you have essentially just an air-cooled condenser. So we want to maximize the amount of time that the unit is able to run in wet mode. Recirculating and reusing the distributed water allows for more operational hours in wet mode. The use of this water distribution system allows us to use the thickest, most efficient adiabatic media pads in the industry. If those media pads aren't being fully wetted, then we have an inefficient system and the potential for scale buildup. Using the recirculating pump and water distribution system allows us to ensure that the pads are fully wetted for more hours of operation, which allows for the maximum temperature depression across the pads, enabling the lowest condensing temperatures possible. Switching gears a little bit, I wanted to highlight some areas where we've seen our customers use the Trillium adiabatic product in their refrigeration systems, specifically CO2 systems. A CO2 cascade system is a combination of 2 centralized refrigeration systems. A low stage or low temperature system, typically consisting of CO2, is cooled by a higher stage, higher temperature system, typically with an HFC refrigerant. And there's a heat exchanger between the 2 systems, so that the high stage system absorbs the heat from the low stage CO2 system. This cascade type system is popular in areas of warmer climates with higher ambient temperatures, because it allows them to ensure subcritical operation of the CO2 system. Typically, there's just a single HFC condenser, and many times designers will include a CO2 desuperheater in terms of a air-cooled condenser or cooler located between the CO2 compressor discharge and the cascade heat exchanger. This desuperheater is meant to reduce the load and size needed of the heat exchanger and also reduce some of the thermal stress of the superheated CO2 entering that heat exchanger. We've seen customers combine these 2 pieces of equipment into one single heat rejection device. You can see the picture on the right. It's a Trillium HFC condenser. And on the right-hand coil, up at the top, there's a small CO2 desuperheater circuit. Where adiabatic cooling really shines in terms of CO2 use is with subcritical operation. Here's a graphical representation of a Sprouts Market in Georgia, where when they switched to an adiabatic gas cooler, after 1 full year of operation, they found that they ran transcritical only 2 hours out of the year. With the CO2 system, whenever you're running transcritical, you're using much more compressor energy. Keeping the system operating subcritical is always the goal. We can look a little bit more closely at this 700 MBH example. You can see that with conditions of 100 degrees dry bulb and 69 wet bulb, the Trillium adiabatic product is still able to achieve CO2 gas outlet temperatures of 80 degrees. Whereas with an air-cooled system, the gas outlet temperature would be 104 degrees. This results in over 40% savings in compressor power. And this really highlights the benefits and the advantage of using an adiabatic type cooler in a CO2 system compared to a traditional air-cooled. Adiabatic can also present many opportunities for retrofit in existing supermarket systems. Replacing an air-cooled condenser and not changing anything else in your system, you can immediately realize lower condensing temperatures, which can mean either a boost in your compressor capacity or just much more efficient operation. It could also reduce peak electrical demand, which could lead to the possibility for some utility incentive rebates with your local utilities. I'll highlight an example of this in one of the case studies to follow. Replacing evaporative condensers or fluid coolers presents a unique opportunity because you already have the plumbing and makeup water infrastructure in place for this type of equipment. Multi-circuit coils are available to match existing systems of evaporative condensers. You could immediately eliminate chemical water treatment systems and the additional maintenance and service contracts that come along with them, and also experience significantly reduced water usage compared to your evaporative cooling products. Here's an example of a retrofit project that we worked on with Roach Brothers. The store was located in Massachusetts and consisted of 3 racks with a combined capacity of approximately 125 tons. Each rack had its own dedicated air-cooled condenser. A study was conducted where a proposal was made for using 2 BAC Trillium adiabatic condensers. One condenser would handle 2 of the existing racks, and then the third would handle the third rack independently. A study was conducted by a local consulting engineering firm, and projected annual savings were estimated at 232 megawatt hours and a peak demand shed of about 35 kilowatts. The consultant worked with the local utility, Eversource, and was able to secure a $75,000 incentive towards the project for Roach Brothers. And Roach Brothers experienced an actual payback of about 1 year for their investment in the equipment. After completion of the project, some observations by Roach Brothers was that they noticed their adiabatic condensers were able to achieve condensing temperatures within about 2 or 3 degrees of ambient temperatures. Contrast that with their air-cooled systems, they were noticing condensing temperatures about 15 to 20 degrees above ambient temperatures. Compressor manufacturers' data suggests that this 20-degree reduction in condensing temperature will yield about 20% reduction in compressor usage. So this turned out to be a really nice project for them. Last, let's look at an example for a Kroger store in Kentucky. The system consisted of 11 glycol-cooled stations with a combined capacity of 67 tons. Their existing evaporative fluid cooler was using an estimated 840,000 gallons of water per year. They looked at a 6-fan Trillium adiabatic fluid cooler that would project to use only 45,000 gallons of water and would allow them to eliminate their water treatment system. Here you can see some before and after pictures from the project, and also Kroger was able to confirm about a 95% reduction in their annual water use, complete elimination and decommissioning of their chemical water treatment systems, and this resulted in approximately $11,000 in annual operational savings as a result of both water reduction and elimination of their chemical use and service contracts. They also noted there was no compromise or no ill effects in their energy bills. So their Trillium fluid cooler was using the same or less energy as the evaporative cooler, while also reducing their water use. I appreciate everyone's interest and time. Please note my email address. I'd be happy to field any questions or speak to anyone who this may have sparked some interest in. Thank you again for your time.